Now I will start the recording and get back to syllabus stuff. Okay. I got off my train of thought for a second there. How you guys doing? Any other questions, concerns, etc. before we get started today? Yes.
So, for the test, is it going to be a combination of like equation stuff and like sort of like scientific questions, like things?
Yes, it'll be a mix of short answer and math. And when I do give math questions in this class, they are always physics math, which is to say I describe a scenario, tell you what's happening in it, and then my expectation would be use one or two formulas to find one thing that I'm asking you for. I'm currently working on the draft, and it would be about half that, about half short answer. And when I say short answer, I do mean short. I don't want full paragraphs. I don't even want full sentences. If I ask you, are these two things third law pairs? And I don't ask you to explain, you can just write yes or no. Yes.
How many questions are your tests normally?
I usually shoot for around 10. Because around 10, and when I write the test, the goal is for it to take students an hour. If it takes me about 10 minutes, being the professor and knowing all the answers, it's to take you guys an hour, because I already know all the answers. And I also do give more points than is needed to get a 100. Like, of the 10 questions, I point out how many points each one is worth, which also helps people know how to prioritize their time on it. Adding up all those point values adds up to more than 100. I don't like giving one bonus question, because if you don't know it, then you don't benefit from it. Yes?
For the formula sheet, do we have to have that printout, or can we make our own?
I wouldn't be opposed to you making your own, but I want to see it first. That said, the only real rules about a formula sheet would be, I ask you not to write the laws of motion on it, because I do want you to be able to point those out from memory. And no worked examples. Put all the formulas, but don't have examples of cases where you've used them. You can write notes about their use and name them, but like, if you wrote out the conservation momentum formula, please don't then have a sample question written there worked out, basically. Now, I will provide formula sheets. Whether you run off a copy of what's posted here or not, I'll have a stack of them up front of the room. But if you run one off yourself or make one yourself, you are allowed to put notes and names and tips all over it. Just no definitions, no worked examples. Like, no defined ones about it. Yes?
Are your test questions like your homework?
Yes, although I would err on the side of them being shorter. Because the homework questions come out of the book, and they're designed for you to be able to ponder them at your own time in a non-test environment. Test questions, I try to write so that they just go faster. You look at it, you know what to do, you do it, you move on.
So this is what the homework was.
Yeah. Because again, the homework, you're supposed to be somewhere comfortable, possibly working with people. Tests is just supposed to be what do you know, what can you do very quickly in a 1-hour environment. You have the full 3-hour lab, but I still write it as if to a 1-hour limit. Any other questions for right now? All right. Now, my plan is to cover between today and maybe about half of Friday, cover the last material that I want you to know for the test. I may end up cutting chapter 7 a little bit short, just because I want to focus on certain things for the test and not bog you down too much. So let's continue on with chapter 7 today. Come Friday and then Monday following, we will spend time going over over everything you would possibly need for the test, and the floor will be open for any review questions that you have. I'm going to post extra practice questions on top of just the normal homework as well that you can just do for extra practice. We can talk about other advice next week as well. Yeah.
We won't be learning anything new like a week from today, right? So if we take the test before Wednesday and we don't want to come to the review session, we're not going to miss anything if we don't show up.
Correct. Let me put the calendar back up. The test dates are 19th, 20th, and 21st, and that's just during lab. So again, you show up for lab in the afternoon. Lecture on these days, technically only Monday and Wednesday. There's no Tuesday lecture. Lecture those days is going to be functionally review sessions, very free form, just helping people with the things that they need help with. If you took the test Monday, got it over with, because you can attend any day of the week, I give you that flexibility for the test. So you can show up at 1:30 Monday, Tuesday, or Friday. Lab, there's a limitation because of chairs, but we don't have the limitation in this room. So if you opt to do it Monday afternoon, or your schedule demands that you do it Monday afternoon, you could skip the Wednesday review session. Now, you should come Friday, because Friday I'll either be teaching or giving back tests, depending on how quickly my grading goes. But lecture these days is review. If you don't feel you need it, you don't have to be here. Does that answer the question? No, I don't take attendance. You're adults. You know what your schedule demands are better than I.
Do we need to let you know if we're going to show up for a different day than our scheduled lab period?
No.
Okay.
I only need to know that sort of thing for lab because of chair and group limits. Yeah, again, for the test, you can show up at 1:30 in this room, Monday, Tuesday, or Wednesday, regardless of whichever lab time you attend. I do the same thing with my exams. The finals, that is. Anything else on your minds? All right. Now for today, let's start working through the Chapter 7 stuff that I'd like you to know before the test. I might end up splitting Chapter 7 in half. We'll cover some of it after the test. I'll keep you posted on that on Friday. I'll make sure the homework is separated between what is on the test and what isn't. When we began Chapter 7, we started talking about energy, how we use it to do everything. Every time you exert force, you are using up energy and giving that energy to whatever you are exerting force upon. The two forms of energy that we have looked at thus far are kinetic energy, the energy of motion, K equals 1/2 mv squared. If you see mass with a velocity, it has kinetic energy and needs that energy to move. The other form was gravitational potential energy, the energy stored in the ability to fall. GPE equals mgh, where g is the acceleration of gravity, 10, and h is current height above the lowest point it can fall to. Now that we've discussed those two forms of energy, I want to start describing the math for what happens when one form transforms into a different one. What I'm about to put up on the board is not a law of motion. It's part of a different set of laws, so you don't have to point this one out on the test. But it is an important concept. It's just not part of that trio. This is the law of conservation of energy, also known as the second law of thermodynamics. So there's a set of laws of motion, a set of law of thermodynamics, and several other laws besides that. This one's technically from the laws of thermodynamics, so you don't have to point it out as a part of the three laws we've gone over so far. You should be aware of it though, because this is the law that states energy cannot be created nor destroyed. It simply transfers between states and between different objects. Bless you. Energy never springs into existence by itself. That energy always existed. It was just somewhere else or in a different form. Likewise, if energy goes away, it does not cease to exist, it has simply entered a different form or entered a different object, possibly that isn't in the system you're examining. To give an example of these interactions, behold the basketball of science. I'm going to place that object right here. And I would like you to tell me what form of energy, if any, this object currently has. Which type of potential? Very good. I prefer the specificity on that one. It currently has GPE because it could fall off this table. It could fall about 1 meter down, so 1 meter. So let's just say it has about 1 joule of GPE, just for simplicity's sake. So let's just say at this position, 1 joule of energy. And we have identified it as specifically being within the gravitational potential form. Now, I'm going to grab the basketball of science and lift it up here. Let's say it's at 2 meters above the floor. What happened to its energy level? It's not a trick, I promise. What happened to the basketball's energy level as I do this? A little louder. Well, what happened to its GPE level? It got bigger. Its KE level stayed the same because velocity zero. Also, its temperature stayed the same. So most of its forms of energy did stay the same, correct. But when I elevate it like this, bless you, it now does have more specifically GPE than it had before. It's 2 meters above the floor now, so let's just say 2 joules at this position. So, we got before, 1 joule on the desk, after 2 joules in the air. That's a difference of 1 joule. Where did that energy come from? Did it spontaneously spring into existence from nothing? No, because the law says it can't. So where does that extra joule come from? Me, my hand. I gave the ball that extra joule of energy. It came from me because I'm the one that grabbed it, exerted force on it, and used up some of my own energy to get it here. That extra joule originated from my arm, the stored energy in my muscles. And that means that I now have 1 less joule in my body because now it's in here. So that 1 joule was not created from nowhere. It already existed inside of me, a different object or a different part of the system. And now I have less energy, so I need to go have a snack and possibly a nap. So that 1 joule difference, energy was not created there. It was simply transformed and transferred from me into the ball. And if you go even further back, that energy was transformed from my peanut butter bagel breakfast and further transformed from some potential state in the dirt that the peanuts came from. So you can trace it pretty far back. Now, we're up here at 2 joules of GPE. What happens to that when I drop the ball? Assume it just stayed on the floor. Let me ask it like this. Once I drop the ball, so I'm going to add a third part to this picture. Is its GPE going to remain at 2? No. Is that number going to get bigger or smaller? Smaller, very good, because its height is decreasing. So as it drops, its GPE goes down. Eventually, at this point, height of 0, GPE 0. So at this point, all that GPE is gone. Was it destroyed? No. What happened to it? It will eventually be transferred into the ground. You are absolutely right. When the ball hits the floor absorbs the energy, and that's often why if you drop like an anvil or a meteor, it makes a crater. Because if the ground has energy, it has to move slightly. So you're absolutely correct. When it hits the floor will gain it. But I kind of want to rewind slightly and examine the moment right before impact. There's technically a moment, if you like, pause time. There's a split second where height is 0, but we're at max speed. The highest speed at which we will hit the ground. At that freeze frame moment, where's all the energy? We haven't hit the ground yet. We're at top speed, height of 0. In the ball in what form? Very good. So in this moment, GPE will be 0. How much KE will it have? 2. Because all 2 joules of the GPE that it had to go somewhere. They have transformed into a different state. This law says sigma energy initial equals sigma energy final. The total amount of energy across all forms before something happens will be the same as the total amount of energy after the something happens. So if the before state is me holding the ball up here, and it has 2 joules of energy in all of its forms, and I drop it, the moment before impact, before the collision changes the ball's energy level, the ball should still have 2 joules, just distributed differently among energy types. That 2 joules remains, just kinetic instead of GPE. That's what falling does. It turns GPE into kinetic before impact. Impact is a different part. Impact is a collision. That's not what we're talking about today. Right before impact, again, freeze frame at that lowest point. One of the purposes of gravity is to turn GPE into KE. And the law of conservation of energy says that the total amount of energy must remain consistent from start to finish. How's that sound? Okay. Let's practice a formal word problem for this. Instead of dropping the item, we're going to show that the reverse happens when you launch something upwards instead. Just to compare to what happens when something is falling. The red numbers and the red drawing on the right have been for this problem. In this scenario, rather than the basketball, we're going to chuck a 10-kilogram bowling ball straight upwards. Don't do that at home, by the way. Don't throw bowling balls. Initially, the ball is going to start on the floor at height 0, and we will consider our initial state to be right after we've thrown it, but before it has time to rise. So it's still at height 0, but we have given it enough energy to have this velocity. And once we unpause time, it will be rising. Well, we just started our stopwatch at time 0, height 0, before the ability to rise has been able to take place. But it has this velocity, and we're going to see what happens to that object as it rises up to some unknown final height. When you throw something upwards, it rises to some highest point. We call it the apex of the launch. We're eventually going to figure out what that apex is, how high the ball will rise based on its initial velocity. But there's one more piece of data I want to point out about this situation, this final situation here. We may not know what that final height is, but a split second, when you throw something upwards and it reaches that apex, for a brief moment, it stops. We talked about this a couple of times. The velocity must hit 0 for a second in order for it to then turn around. Because if the velocity initially points up, that number gets smaller all the way up here until it hits 0, and then it becomes negative on the way down. It has to hit 0 at that point, or else it doesn't turn around. So at that highest point, we don't know what that height is, but we know that at that point, the final speed must be 0. So that's an assumption that we can make to give us one more number to use. Again, this happens every time something is launched upwards. At that highest point, its vertical velocity drops to 0 before continuing down. Does that sound all right? All right. I gotta stop throwing my markers around if I want to use them. So that's the drawing for the scenario. I've also got all the variables listed over here again. I'm going to put in the math. Any questions or issues before we do the math part? All right. To start with, what form of energy does the ball have initially? Right here, height 0, velocity 4.5 meters per second. What form of energy do we need to give it so that it will launch off the floor? Kinetic. If it has mass and velocity, it must be in the possession of kinetic energy. So it must initially have some amount of kinetic energy. Remind me the formula for kinetic energy.
Mass times velocity squared times
Yep. 1/2 mv squared. If we're specifically looking at the initial kinetic energy, I'll just specify initial velocity. Now separately, just to kind of prove that the object doesn't have any GPE at this point, what is the formula for GPE? Mass times gravity times, very good. And if we're specifying initial GPE, we'll use that initial height of 0. So, we suspect the ball must have kinetic energy here at the start. So we'll use this formula to find out how much kinetic energy that is. That's the second question. 1/2 times the mass of the ball times the ball's starting velocity squared. You want to make sure you're only squaring the velocity, so just be careful how you put that in your calculator. I tend to do, as I wrote it here, open parentheses, number, squared, close parentheses. And that'll give us the initial kinetic energy level of the ball. And just to compare, I'll also calculate the initial GPE. Whoops. Ten times 0. On the floor, the bowling ball has no GPE. How much kinetic energy does it have? It has 0 GPE, because its height is 0. How much kinetic does it have, based on this formula?
101.25.
Thank you. 101 approximately joules. So, currently, all of its energy is in the kinetic state. It hasn't had time to rise yet. We kind of froze time right there at the beginning. Initially, it's got nothing but KE. And so its total energy level, again, we're thinking of the total energy level that must remain the same from start to finish, that total would be these two different types added together. 101.25 plus 0 is 101.25. So this is all the energy it has right now. Bless you. And that is the initial state. Any questions about the initial state? The first two parts here. Okay. Next, what is going to happen to the form of energy that the ball has as it rises? What's going to happen to that kinetic energy level as the ball elevates? It will decrease. You know this because the ball has to be slowing down on the way up if it is eventually reaching a velocity of 0. Gravity is going to cause the ball to accelerate and change its velocity from 4.5 to 0. If the ball's velocity is decreasing, its kinetic energy level must also be decreasing, since velocity is part of this formula. The v-term gets smaller, the ke gets smaller. Now, as that ke drops, is that energy being destroyed? No. What is instead happening to it? Transformed into... Very good. Because as the ball's velocity goes down, its height is going to go up. And so the act of rising is a transformation of ke into GPE, which we will now demonstrate mathematically. So all of this here, this was the initial state. This was the initial ke and the initial GPE. We're now going to switch gears and look at the final state instead. We're going to do that using the conservation of energy formula. It's very similar to the conservation of momentum formula. Except instead of the momentum formula over and over again, we need to add together all the different types of energy that the ball can have both before and after. So the initial side, we've only studied two types of energy. The ball's total energy level will be the sum of all of its energy types initially. We've already found these variables. We know its GPE initial level and its KE initial level. We have these numbers. So we have the initial half worked out already. Afterwards, those types of energy are going to change. And so the ball will have a different final KE level and a different GPE level. But what this law says is that the total must remain the same across both sides. Again, similar to how the momentum total remained the same across both sides, even if it was distributed differently between the objects. Questions at this point? KE initial, we've already determined that value. We know the object's initial kinetic energy level. We also know its initial GPE level. So again, the total energy level of the ball is 101.25, and that total will remain unchanged. But now let's look at its specific KE levels and its specific GPE levels at that highest final point. At that highest point, if I plug in the KE formula, we've already said that its velocity at that height is 0. So its final KE is going to end up being 0. Because at that highest point, it stopped. There's pausing time right there. Now its GPE level, so again, just using the GPE formula, it's going to have GPE because it's going to be at some height, we just don't know what that height is yet. But this law requires that that height be big enough such that the same total amount of KE that it originally had is now able to fully transform into GPE. Basically, if we kind of eliminate the things that are zero, we're comparing the initial KE level to the final GPE level, showing that the energy changes states from start to finish, but the total remains constant. How's that feel? Any questions or issues? All right. This will allow us to calculate what that final height is, because we know the object's mass, we know gravity on this planet, so we can figure out the height at which it will have this much GPE. I'll just simplify this a little bit by removing the zeros. So, GPE initial 0, KE final is 0, if our final velocity is 0. And this is meant to show again the transformation of KE into GPE as the rising process takes place. And we can then solve for HF, which should be about 1.0125 meters, which is not very tall, not very high up actually. Don't throw bowling balls. So, I'm going through these again from start to finish. We initially have KE. Figured out how much KE we initially had. That KE is going to turn into GPE on the way up. And that final GPE total will still be 101.25. And it will be at a certain final height where all that energy is able to fully transform into the GPE state. This is basically the reverse of what happens if you start up here and fall down. When you start up here, your GPE turns into KE. And in fact, if we, unpause time, that process will continue. The bullet ball will fall back down. GPE turns back into KE during that process. So the act of being a projectile, falling while moving both up and down, is the act of your energy levels changing. It happens both on the rise and on the fall. It's just on the rise, you go from KE to GPE, and on the fall, you go from GPE to KE, but the level of total energy at all points remains constant, even if you look at some weird middle point in between. If you were to examine an in-between point, you can observe the KE draining and the GPE rising by the amount of KE that loses. I visualize it like bars on a graph like this sometimes in my brain. As you elevate, the KE drops and the GPE rises by the same amount. And the reverse happens on the way down. Questions, concerns? All right. Now, energy transformations like this happen all around us. And in fact, every time you do anything, you are causing causing energy to transform between various different states. Every action you undertake involves the transfer and transformation of energy. And the term that we use to describe those actions in which energy is transforming is called work. So this is probably the last vocab word for the week. The physics term work is just the word described for the use and transformation of energy. Anytime energy is transforming, like it is here, work is the reason why. And in order to do work, you have to exert force on an object while it is moving. Any force is capable of doing work. And in fact, every time your body uses any amount of force to make anything move, that includes parts of your own body, you are doing work and using up your own energy. The purpose of this formula, work equals force times displacement, is to tell you how much work you accomplish within a specific action, which is equivalent to saying how much energy you have to use for a specific action. The physics definition of work is the use and transformation of energy, but that also can tell you how much energy needed to be used to accomplish the specific task in question. If you move anything, like if I pick up my own water bottle, I have to exert force on it, and it now moves some distance outwards. According to this formula, I have now done work. I have used up my own energy level and given energy to my water bottle in the form of GPE. It has more GPE now than when it began because I gave it that energy from my own muscles, and now I don't have it anymore. Every time you exert force, you use up energy because of this formula, and that is why using force will eventually tire you out. The more force you exert, the more work you do, the more energy you use up. And then you have a snack and take a nap. How's that feel so far, just as definitions go? Okay. If you wanted to, you could take advantage of the physics definition of work if someone asks you if you've done your work yet today, because all you have to do is this, and then you can honestly say yes. And again, this technically happens for everything in your body that exerts force. That includes your heart beating, your eyelids blinking. Talking involves force. You have to push around your vocal cords and push air out of your lungs. Again, everything you do exerts force to make something move, and therefore everything you do is work and takes up energy. And that's why we have to keep eating. So, new formula. The W on the front is the work. Since work is just energy used, it's basically just another variable talking about energy. So kind of just another form of energy like KE or GPE. And for that reason, it's still measured in joules. There's a lot of things measured in joules in this class. The force is, again, still a force measured in newtons, and the delta X is displacement. You have to push on something and then it has to move some distance. That, again, does include moving your own limbs. But as long as you are using force and making something move, you are doing work, accomplishing a task, and using up your own energy. Now, this is a new formula, so let's get a small amount of practice for it. we are going to push a box across the floor. We will exert a force of 50 newtons to the right, and the box is going to displace 10 meters within the x-axis in the same direction as that force. Separately from those two vectors, the box also weighs 100 newtons. So, my first question, given these three numbers, how much work do we accomplish pushing this box around?
$500
500, that's the right number. What is the unit of work and energy?
joules.
Joules, very good. So remind me, what is the formula for work from the previous slide? Thank you. I will talk about the parallel in a second. So, to find the work that we accomplish, I'm just going to call that work me. We take the force we exert, multiply it by the distance the object moved because of that force, and that tells us that we accomplished 500 joules of work in moving this box. We gave the box 500 joules of energy that we now don't have anymore. So every time we push that box this distance, we lose another 500 joules and eat a snack, take a nap. All right so far? Okay. Now, you pointed out there's this parallel symbol in the formula here. This is attached to the force and it's a subscript, so it's, if I was to read this out loud, it'd be work equals force parallel times displacement. That parallel is a little restriction on the cases where this formula works correctly. There's a requirement that the force and the displacement be parallel to each other. Using this scenario as an example, this 50 newtons points horizontally to the right in the positive x direction. This displacement is 10 meters to the right, positive x, horizontal axis. These two things are parallel. They point in exactly the same direction. And so the formula works in that scenario. My next question then would be, we have a different force that is currently acting on this box, because you can't really escape gravity on this planet. This is going to be here, whatever we do. How much work does gravity do on the box, given this restriction? Gravity pulls down, and the box moves to the right. Is gravity the thing accomplishing anything here? No, we're the ones accomplishing something. We're the ones making the box move with our rightward pointing force. The downward pointing force of gravity accomplishes nothing in this scenario. That force is perpendicular to the displacement. As a refresher, perpendicular, right angle. Down is perpendicular from right. And so there's kind of two ways that the formula works out in that scenario. There's two ways that you can describe it. So I'm going to write here WG for work gravity. The force of gravity is 100 newtons in the y-axis. Now, we would have to plug in a y-axis displacement for the formula to work right, given that parallel description. What is the box's y-axis displacement? 10 meters is an x-axis variable. So the box's y-axis displacement is 0. Gravity accomplishes 0 joules worth of work. The other way you could think about it is if you wrote the displacement part first. This displacement is an x-axis displacement, so we would have to consider the x-axis force that gravity exerts. How much force does gravity exert in the x-axis? None. Gravity will never pull sideways. So gravity's x component is 0, and that's another way that gravity does no work in this scenario. It's there, but it's not really doing anything. It's not contributing to us pushing the box around. Does that make sense? All right. Now, gravity is capable of doing work. It's just in scenarios where the displacement is vertical. Like this one. Gravity is the force responsible that does the work to transform KE and GPE back and forth into each other as something rises and falls. This happens because of work. The work of gravity is what's transforming the energy through this process. Just like over here, our force is transforming our muscle chemical energy into kinetic energy in the box. But every force can do work as long as the work and the force and displacement are parallel. And frustratingly, this is what we'll talk about on Friday. Frustratingly, that includes friction. Friction is the pest that makes life on Earth hard. It takes energy away and does negative work. And we'll do that on Friday before we enter testing. Questions? All right. It's a wonderful day. Let me know if you need anything. I sent them in the wrong order. Sorry to say I don't know, but I mean, be finding out.